Hello, and welcome to Team 10's MEng Group Project Video Demonstration Executive Summary for the e-Agri Pocket Agronomist. Let's meet the team.
Hi, my name's James, and I'm in charge of the firmware, and I'm also the project manager.
Hi, my name's Abby. I'm in charge of image processing, and I'm also the secretary.
Hi, my name is Mustafa. I'm in charge of the housing design and smartphone app, and I'm also the auditor.
Hi, my name's Russell, and I'm in charge of electronics and Bluetooth firmware.
Hi, my name is Matthias, and I'm in charge of machine learning.
The Pocket Agronomist is a device intended as a supplement for farm management, using smart technology to assist farmers in the decision-making process of treating their crops to maximise their yield potential. The device uses multispectral imaging to take photos of crop leaves and determines if they are infected or uninfected, displaying the result using a traffic light system and providing more information on an app. The overarching aim of the project was to produce a marketable product suitable for handheld use based on previous iterations that was smaller and faster, with the addition of advanced image processing and machine learning techniques, focusing on improving the user interface. The motivation for this device is to assist the reduction of the contribution to climate change from the agricultural industry. With a growing world population, increased demand on yield leads to rising pressures on farmers to fulfil the demand, which in turn leads to more consequences for them, mainly financially. To mitigate this, many farmers are over-fertilising their crops. Roughly 25% of nitrogen goes back into the atmosphere on farms. Specifically, this project aims to provide farmers with a more convenient, comfortable, and user-friendly solution compared to the previous generation device, which was larger, slower, and less comprehensive. Additionally, the data taken from the plant images can be used for further research in the field of nutrient detection using multispectral imaging, as the 15 wavebands have been designed into the hardware to enable further work. If findings identified wavebands with additional uses, the device will be able to take measurements of them without any alteration to its hardware design. Immediate further work would include physical construction of the device and a collection of a larger dataset. Additionally, the use of cloud storage would be developed. Migrating the database off the Jetson and onto a cloud server would allow app synchronization and thus reducing the power demand from the device. The project was broken down into more manageable aims to ensure all segments were completed fully and to a high standard, each of which belongs to a subcategory of either firmware, software, or hardware. Once relevant literature was studied on plant science, image processing, and machine learning, the previous generation was analysed by observing the C++ firmware code for multispectral application to provide a starting point. Following this, firmware using the Jetson Nano system is created in Python to reproduce the previous generation's functionality, while allowing faster data collection and algorithm processing. A new image processing algorithm is to be developed that automatically detects leaves from the images. From this, the spectral reflectance value for each wavelength is calculated. To allow training and testing of the machine learning algorithm, labelled datasets are to be created from the existing images of cassava brown streak disease. A new machine learning algorithm is to be produced to accurately classify the infection status of a leaf to lead to a traffic light system indicating the result. The design of an intuitive and user-friendly graphical user interface, including the production of a smartphone app for meaningful representation of data. Additionally, the build-up of a history of readings without increasing the cost of device components is made possible by allowing the Jetson to communicate with a smartphone via Bluetooth, adding GPS and timestamp data to readings using the phone's GPS and clock. The redesign of the LED array to reduce the overall device size and increase its portability. Implement power management features so that the system can collect, store, and process reflectance mode MSI data for one field from a single battery charge. Finally, the design of an injection molded assembly that would be useful for bulk manufacture. The final result of the project was the creation of a convenient handheld device that provided accurate infection detection using a user-friendly interface. The size of the device was reduced by 71% by using a modular design. The power consumption was managed such that the device lasts over 12 hours when taking a reading every 2 minutes. A traffic light system was implemented to further improve the user experience to indicate the condition of the leaf. The processing of raw images was automated and successfully detected the leaf, leading to accurate values of spectral reflectance. These values led to a machine learning algorithm with 87% accuracy and 94% precision. Compared to the previous device, the complete time to take a reading was reduced by 80% to 4.8 seconds. The device's overall marketability was greatly improved as the shortcomings of the previous generation have been addressed and additional functionality added, taking into consideration the criteria from the industry sponsor along with feedback from professional farmers and agronomists. The device was shortlisted as a finalist to the competitive Venture Further competition in the environmental category, further highlighting the impact factor of the device and its economic and societal benefits to the agricultural industry.